Okay, so we've got just a little bit left to cover, two theorems in particular. And again, I said this earlier on in the first video for this section. This particular introductory section to orthogonal matrices does not have a lot of examples that we work through. Your book goes into depth on a few examples. I would encourage you to read those, but the primary thing is this sequence of theorems that we're coming up with. And again, I know I already said it in the previous video, 7.2 is going to be a little bit more example heavy, where we talk about orthogonal diagonalization of a matrix. That's a mouthful, I know. But anyways, let's go ahead and wrap things up with these last two theorems. So this one says that if you have an inner product space V, and if you have an orthonormal basis for that inner product space, and we're calling that basis S. And if you were to take any two vectors in V and find their coordinate vectors relative to S. Remember, coordinate vectors in this case are going to be vectors in Rn, where the components of that vector represent the scalars that you would multiply the vectors of S by in a linear combination to get either U or V. If we have all this, then the norm of U is equal to the square root of the sum of the squares of the components of U. The distance between U and V is defined or is evaluated this way, and the inner product of U with V is evaluated this way. Now, if you read this too quickly, you might look at that and think, yeah, I already knew that. Isn't this how you evaluate norms, distances, and inner products? And the answer is no. That's how you evaluate norms, distances, and inner products if your inner product is the dot product. Remember, the more general case for norms and distances are defined in terms of whatever your inner product for an inner product space happens to be. So what this theorem is saying is that if you are using the coordinate vectors for an inner product, for vectors in an inner product space, and those coordinate vectors are relative to an orthonormal basis, then the norms, distances, and inner products of those vectors can be evaluated using basically the exact same tools as the dot product case, or the Euclidean inner product case. Okay, so why is this true? Well, your book says leave these proofs to an exercise. I'm going to prove one of them. I'm going to prove part C. If you can prove part C, then parts B and A are kind of consequences of that. You can see it that way. So let's think about this for a moment. Let's let our set S be an orthonormal basis for V, and these are the vectors in S, W1 through Wn. Okay, now what I want to do is think of the coordinate vectors for U and V relative to this basis. So U1 through Un, that's the coordinate vector for U, V1 through Vn, coordinate vector for V. Remember, by definition, what it means to have these as coordinate vectors is that the vector U is equal to this linear combination. The scalars are the coordinates of US, or U relative to S, and similar with V. Okay, so we can represent U and V as linear combinations of those basis vectors. Now, I'd like to take a look at what this inner product would look like with this information. So the inner product of U with V, I can represent U and V as linear combinations in this form. Suddenly this inner product gets really, really big and really, really messy. If I use my additivity and homogeneity properties on this first component in this inner product, I can split it up into a total of n inner products, one for each term here, and I can also pull the scalars out. So my very first inner product, my very first term is going to look like U1 times the inner product of W1 with the rest of this. So remember, the second component, I haven't done anything with that. It's still going to look like that linear combination that's equal to V. Then I would have a U2 come up next with an inner product of W2 and then all of this. I didn't have enough space, so I didn't put that in there. And there's going to be a total of n of these, ending with UN dotted with, I said that in the second case that I would have, I do have a typo. This should be WN right there. So a total of n of these. Now if I do the same thing with each of these n vectors, but take the second component and break them up using those properties of additivity and homogeneity, which we know we can do. We proved a theorem saying we could do that. Then each of these n terms up here is going to become n more terms. So I have n times n terms in total here. And it makes this gigantic sum. Okay, so this first term here is going to explode into this row of n terms up here. And using homogeneity, if you think about it, I'm going to have u1 times v1 times the inner product of w1 with w1. That's my first term. Then u1 times v2 times the inner product of w1 with w2 here. And then so on and so forth. And then I do it again for the second term here. It's going to explode into a sum of n terms. And then I keep doing that until I've done that to every term up here. Remember the assumption that we made in the first place. S is an orthonormal basis. So what that tells me is that of all of these inner products, anytime I have an inner product of a basis vector with itself, that's going to give me a norm of 1. That inner product will equal 1. So you can see where those are happening. It's going to happen along the diagonal entries in this little, looks like a matrix that I made. W1 with W1, this inner product will be 1. W2 with W2, this inner product will be 2. Wn with Wn, that inner product will be, sorry, I said 2, it'll equal 1. This inner product will equal 1 as well. 1 times those coefficients are going to leave me with a U1 V1, U2 V2, Un Vn, which you're seeing here. Okay, but what about all of the other terms? Well, again, if it's orthonormal, that means it's also orthogonal. So if I take the inner product of any of these vectors with any of the other vectors in S, those will all go to 0. So that means there's nothing else except for these n terms right here. And that's what part C of this theorem is saying. Okay? Last theorem. Let's go through this. So let V be an n-dimensional inner product space. Here's where we want to talk about the change of basis idea. If P is a transition matrix from one orthonormal basis for V to another, then P is an orthogonal matrix. Okay, so we're going to use a couple of things in this proof for this theorem. One is the theorem that I mentioned earlier, where there's some equivalences that are important. I'll pull that up again. We're going to use these two equivalences here, A and B, that an orthogonal matrix, or A is an orthogonal matrix if and only if this statement is true. I'm also going to use this previous theorem right here. So coming up here for a second, this norm right here, I'm going to be calling that this in this proof. The norm of U relative to V. And what I mean by this is the norm that you would normally use with whichever inner product we define for V. When I don't put a subscript outside of the norm like this, I'm implying that the norm is the Euclidean norm, meaning the norm that you evaluate when you have a dot product of a vector from Rn. Notice the vector in here, U is not the vector in here. It's the coordinate vector of U relative to S. That makes this thing a vector in Rn, so it makes sense to take the Euclidean inner product of that thing. This theorem, part A, is saying that this norm will equal this norm. Okay, just by giving you a kind of a formula, but it's essentially saying this. So we're going to use that fact in this theorem. Okay, so I make that note here. If we use an inner product with no a norm with no subscript, it's the Euclidean norm, meaning the normal one that we think of with the dot product. And then if I put a subscript down here of V, then we're talking about the norm that would come from the inner product of V. I'm also going to let B and B prime be orthonormal bases for V, and P is going to be the transition matrix that takes us from basis B into basis B prime. This is from chapter 4, where we talk about transition matrices for change of bases. Now, I'm going to let U be any vector in V, and we're going to start using that previous theorem. So the norm of U relative to V, according to our theorem up there, is equal. I'm using this, it's equal to the Euclidean norm of the coordinate vector of u relative to b prime. And we know this because the previous theorem says as long as this basis is orthonormal, this is true. We assumed b prime was orthonormal. B is another orthonormal basis, so the norm of the coordinate vector of u relative to b would also equal the same thing as this. Okay, so we have this identity or this equality here. But there's a different way that I could have gone about this. Also, norm of u relative to v is equal to the norm of the coordinate vector of b prime in the Euclidean norm. Same two steps here. But instead of using a property of norms, I'm going to use the definition of a transition matrix. Remember, the coordinate vector of u relative to b prime could have been obtained by multiplying the transition matrix on the right by the coordinate vector of u relative to b. Remember, that's the job of a transition matrix. It takes coordinate vectors relative to b, turns them into the corresponding coordinate vectors relative to b prime. So I could have changed this vector into this guy right here. Now, both of these things are equal to the norm of u relative to v, so I could set them equal to each other. Okay, and we're almost to the point where we can use that previous theorem to show that P is an orthogonal matrix. Let's let X be any vector in Rn. Okay, and we're going to let U, that should say U in V. U is going to be a vector in the inner product space V, satisfying this. Now remember, for any vector in Rn, that vector will represent the coordinate vector of some vector in V. So I'm saying let's let U be the vector in V that has X as its coordinate vector. Okay, then the norm of U in the Euclidean inner product. This should be norm in the inner product relative to V will be equal to the Euclidean norm of X, which is equal to the Euclidean norm of Px because of this equality right here. Therefore, P is orthogonal because, remember, if this is true for every vector x in Rn, according to our previous theorem, that's equivalent to the statement that this matrix is orthogonal. Okay, that's going to be it for 7.1, relatively short section, but some of these results are going to be useful in 7.2, where again we're talking about orthogonal diagonalization. Try saying that 5 times fast.